Okay, now that we know how to formulate good hypotheses, they're testable statements, they make a prediction, and the variables that we are testing are clearly and specifically defined using operational definitions. Now we can get to the fun part. What is measurement? So we're starting with something that we've talked a little bit about before, is before we can define measurement, we have to define variables because variables are the things we are measuring. So, as we mentioned before, a variable is any quantity or quality that can take on a range of values. For example, if my hypothesis says that older children will be more independent than younger children, I have two variables there. I've got age of children, and independence. I have to sample children from a variety of ages. Hey, variety sounds like variable too. What does that tell you? I have to sample children from variety of ages. I have to have a variable with a range of values for age, or I can't even test my hypothesis. If I only test one age of child, how will I be able to say that older children are more independent than younger children? So one thing to always remember is a variable must vary. And it follows that because the values vary, we can assign numbers to indicate the amount of some variable present. So because we have that variation, we can assign numbers to indicate the amount of that variation. For example, with age, younger children have lower numbers, 1, 2, 3, 4-year-old. Older children have higher numbers, 6, 7, 8, 9-year-olds. So the ages are assigned numbers, and the numbers represent something. So measurement is the process of assigning numbers to variables. Now before we get into that, I'm going to take you sort of into outer space for a minute. This is very theoretical, but I think it's really fun if you've never thought about it before. So before we're going to talk about measurement, we're going to go over some of the properties of the abstract number system. And if you've never thought about the properties of the abstract number system before, now is the time to do so. It's absolutely fascinating that how much we take for granted with numbers that we use every single day. So I'm going to go over these 4 properties that are listed on the slide. And keep in mind that they're listed in order, top to bottom, most simple to most complex. So let's start with identity. Identity is what a number does, and it's when a number identifies something. So for example, the number 1 means the number 1. 1 identifies 1. There's no other number that 1 can be. Or for example, a great example of this is sports stars. Athletes have certain numbers that represent them. Their numbers are their identity. And don't laugh at me, I really don't know athletes' numbers because I don't remember. I believe that Kobe Bryant started his career out as a number 9. So at that time, 9 meant Kobe. Okay. I think O.J. Simpson was 32, even though I'm not 100% positive. So at that time, 32 meant O.J. So that's an example of numbers identifying something. You've got a number representing the identity. Okay, that's pretty straightforward as long as you get your head around it. The next one is magnitude. Numbers are in order. Larger numbers are greater than smaller numbers. So one is less than 2, which is less than 3, which is less than 4. So we know as we go higher up the number scale, we're representing more quantity. And as we go lower, we're representing less. That's the property of magnitude. The third thing that the abstract number system represents, or that numbers represent, are equal intervals. Using our numbers, we know that the distance between 1 and 2 is equal to the distance between 2 and 3, which is equal to the distance between 3 and 4, etc., etc. And this equality of distance is great because it allows us to subtract without fear of making a mistake. So because the distances are all equal between numbers, we know that if we have 10 oranges and Johnny takes away 3 of those oranges, we have 7 oranges left because those distance between the numbers is equal. And that's known as equal intervals. And then the final property of the abstract number system is that our abstract number system has a true zero. And what I mean by this is that 0 equals nothing. So when we say 0, we mean nothing. I mean, we mean the construct nothing. So if there's a plate of cookies on the table and you're sitting in the kitchen and your mom comes to the table and says, "How many cookies did you eat?" When you say 0, it means that you didn't eat any, assuming you're telling the truth, of course. But 0 means 0. So now that we've got those 4 properties of the abstract number system, and if you understand those, you can take a nap for the rest of the lecture. Well, don't take a big nap, just listen. But once you've got those down, you really understand the rest of the lecture. Identity, magnitude, which is order, equal intervals, which is equal distance between numbers, and true 0. 0 actually represents an absence of the quality. So because we know those 4 qualities of the abstract number system, these next scales of measurement are going to be a snap. And what these scales of measurement are is a choice we have. So we said that measurement was assigning numbers to variables. Well, we can assign numbers that mean one or all of those 4 abstract qualities. And let me explain them to you. And remember, keep in mind that they go from simple to the most complex. And if you're trying to memorize them for the test, which I would recommend you at least know the order, they spell out noir, N-O-I-R, noir, and that's the French word for black. Or if you like wine, it's a fine wine, Pinot Noir. So remember noir, that'll help you when I go over these scales of measurement. And remember, I'm going from simpler to more complex. Nominal scale. Each number represents an arbitrary category label. Data on the scale is either called nominal or categorical data. So sometimes I'll use those terms interchangeably. Nominal and categorical just mean the same thing. And they have the mathematical property of identity. So the example I gave for this that I still think really holds is an athlete. The number on an athlete's jersey is nominal data. It doesn't really mean anything. Athletes with higher numbers aren't better than athletes with lower numbers. The number is just something we assign to keep track of them, so we can measure them, so we can use statistics and do all of the other things we like to do with empirical data. Another great example of nominal is when you do a survey and you assign numbers to answers of the survey. So let's say, for example, you ask people, what is your race? And you don't know that much about race in Hawaii or intermarriage, and you just give them three choices: white or Caucasian, Asian, or African American, or black. So you give them three choices and you give them numbers 1, 2, 3, just in the order they answered. 1 is white, 2 is Asian, 3 is black. Does that mean that black is greater than Asian, that's greater than black? No, you're just having numbers identify the racial categories. Same can be said for religion, which is something that you can be asked on a questionnaire. 1 for Catholic, 2 for Protestant, 3 for evangelical. It doesn't mean that Catholics are worse than everyone else. It just means those are the numbers that we are assigning to those variables. So that's nominal, and that's very possible. And you'll have some demographic questions in our questionnaire that are on a nominal scale. Male and female, nominal. Male, female, other, nominal. So that's just when the number reflects an arbitrary category label. So moving up in complexity, we've got ordinal. And this is crazy easy to remember because ordinal is in order. So something on an ordinal scale reflects the order, but not the amount of a variable. This is ordered data, and it has both the mathematical properties of identity and magnitude. Because these only not go up in complexity, but everything on a higher scale has the properties of a lower scale as well. So this has both mathematical properties of identity and magnitude. And the easiest way to explain this is to think of rankings. So the very first time I took research methods, I think I told you guys I've taken it a bunch of times before I taught it. The very first time I took research methods, it was a college class, and they had us bring pictures of our stuffed animals. We brought pictures of our stuffed animals to class, and then we had a stuffed animal beauty contest. We saw which student had the most beautiful stuffed animal. We ranked them. Everybody ranked the stuffed animals. I think there were 10 people in our lab from 1 to 10. And then we figured out the overall rank order. And so the top place stuffed animal was rated first. The second place was second. The third was 3. The fourth was 4, et cetera, et cetera. Now that's in order. We know that 1 was the favorite one, but we really don't know if, just from those numbers, we don't know if second place was really close to first place. It had almost as many votes, or it was second place, or first place totally took it away. We don't know. We don't know the distance on an ordinal scale. Or my other favorite example that I would use if we were live, I usually have a couple of athletes in the class, and sometimes football players, sometimes baseball players, sometimes volleyball players, softball players. I usually have a lot of athletes in this class, and I'll have the athletes raise their hand, and I'll pick 2 of them. And we'll have the 2 athletes and me, and we say we all got in a running race. Well, sadly, what's going to happen? Those athletes are going to annihilate me, right? So they're going to be way at the end of the race, 100-yard dash. Well, I'm still at the beginning, just panting and puffing. So in that case, we would have the athlete who got there first would be first place. The athlete who got there second would be second place. And then I would probably get there about a half an hour later, asking for an ambulance and a lot of water. Well, not that bad, but yeah, maybe. So in that case, athlete number 1 would come in first, athlete number 2 would come in second, and I would come in third. So we'd be numbered 1, 2, and 3. Do you think the distance between the times we come in would be equal? Of course not. The athletes would be in like half an hour before I am. So that's another example of an ordinal scale. We know there's an order. We know there's an order, but we don't know. I mean, it's not equal between the places or the numbers. Okay, that's our second scale of measurement. Nominal, we have ordinal. Now we're starting to get a little more complicated, and that's interval. And that indicates the amount, but has no 0 point on the scale. That's often score data. It has mathematical properties of identity, magnitude, and this is the new one, equal intervals. And the one I like to use for this is a score on a test score for a class. No, actually, no, that's not a good one. As an IQ score. So the IQ score is designed so there's a formula, and the more questions you get right, the higher your score is. And the distance between the questions is exactly equal. You get a full question right or a full question wrong. So if I get a 10 on the IQ test and my brother gets a 5, I am 5 points higher than he is. Exactly, there's an equal distance. And let's say my cousin gets a 15. The distance between me and my cousin, 10 and 15, is the same as the distance between me and my brother, 5 and 10. So an interval scale allows us to make comparisons and differences between numbers because we know that these tests or objects are constructed such that there's an equal distance among them. Another example might be whole numbers. So if I'm observing behavior and one participant sneezes 4 times and the other participant sneezes 3 times, I can be sure that there's one sneeze between them, one full sneeze, which is, and the first person did 3 and the second person did 4. So equal intervals. So now we've done 3 scales of measurements. NOI, nominal name, ordinal order, interval, distance between. Now we're at our last one, and that's a ratio scale. And this scale has a true, zero, and equal intervals, just like the real number system. The ratio scale is the whole burrito. It's everything. It's everything that the abstract number system has to offer. It produces score data, and it has the mathematical properties of identity, magnitude, equal intervals, and a true zero. So let me give you an example of that. I'm going to give you a couple examples. The first one, and the one you'll see in probably every research methods or statistic book you ever open, is temperature. And at this point in class, I usually find a student that's from somewhere really cold. Like I've had students before from Alaska or Minnesota. And I ask them, if it's 0 outside, what is that temperature like? And they usually say, it's freezing. 0, either Celsius or Fahrenheit, is pretty darn cold, okay? 0 is cold. And I say, does that mean there's an absence of temperature? And they say, of course not. It's really, really cold. 0 is just, in our temperature scales, both Celsius and Fahrenheit, 0, well, in Fahrenheit, it's more of an arbitrary number. Well, it's freezing, based on freezing. And Celsius, Fahrenheit, it's not based on freezing. Celsius, no, well, Fahrenheit, never mind. This is not chemistry, whatever. So anyway, the point is that those are not ratio scales because 0 doesn't mean an absence of the quality. In a ratio scale, 0 means the absence of a quality. Now, back to you eating cookies. And if you tell your mom, no, I didn't eat any cookies, 0 means no cookies. And so in that particular example, the number of cookies you ate, that's a ratio scale because 0 means nothing. Temperature is not a ratio scale because 0, even at a 0 temperature, there is some temperature. Another example would be IQ, and that was the one I mistakenly almost gave you. An IQ is not a ratio scale because if someone scores and is 0 on an intelligence test, does that mean they have 0 intelligence, that they're just a log? No. anything living by definition has some sort of intelligence. So intelligence, or IQ, is not a ratio scale. Now I'm going to stop right here because I've taught this class. Every time I teach this class, people get really confused between interval and ratio scales, because that true zero is kind of a judgment call as to whether zero actually means an absence of the quality. I mean, you might even say, well, what if the person taking the IQ test doesn't even pick up the pencil? Well, in that case, you might say they don't have any intelligence because they didn't even attempt the test. So it's kind of a judgment call, and it's more theoretical, the difference between interval and ratio scales. I will not ask you for an example of interval and ratio scales. It's important in advanced statistics because a true zero is necessary to perform division. But where you are right now, it's not quite as important. It's more of a theoretical or super advanced importance. So I will never ask you of an example between interval and ratio scales, because I've seen that students just can turn themselves inside out and waste time on thinking of that, when I'd rather have them get the basics down. So I will never ask you an example of a ratio scale. I won't give you an example that's tricky, but I do want you to know that interval means equal distance and zero is arbitrary. So interval is equal distance and zero is arbitrary. Interval is equal distance and zero is arbitrary, while ratio is everything. It has equal distance and zero means an absence of the property. Okay, there we have it. NOIR, nominal ordinal interval ratio. Here's a little chart that I made to help you recognize that. So those of you who have the capability, you might want to stop this recording and take a picture, because this will really help you study for the test. And these are our scales of measurement: nominal, ordinal, interval, ratio. So the next question might be, why in the world did I spend half a lecture talking about these theoretical scales of measurement? Well, they are critically important. And why are they critically important? Because the statistical tests you can use on your data depend upon the scale of measurement of your variables. And as you get into collecting data and analyzing data, your GAs are going to help you with this, but you need to know the scale of measurement of your variables in order to run tests that make sense. So after a while, it just becomes automatic. You automatically know your scales of measurement, and so you can run the right test on them and be the most sure that your results are not due to chance. So thanks for sticking with me on our measurement lecture. I will see you again for our next lecture, which is going to talk about how we can make measurement the highest quality that we can. See you soon. Bye.